Okay, so thanks everyone for coming. This is the second review session, second and last, for 127. And today we're going to cover a selection of problems from past exams, which are about the post-midterm content. Roughly speaking, this goes from duality to KKT, a variety of classes of optimization problems such as LPs, QPs, SOCPs, and then some algorithms like I think there's a problem on Newton's method. I forget if there's a problem for coordinate descent. So that's today. So I apologize for the mistake, but there's a bit of a printing mistake, which means that the last two problems are going to be covered after the first two problems. Oh, did this die? Okay, no. Last two problems are going to be covered right after the first two problems, and the middle three, I think, are going to be covered at the end. But it'll make sense, and we'll announce the problem numbers like when we get there. The other thing is that the other thing is that we're kind of front-loading the difficulty for this worksheet, and that the first problem is going to be the hardest, so don't get too intimidated. The first problem is like probably one of the harder problems on like any past exam for this class. So let's work through it. Okay, so the first problem is going to be about duality. So first of all, the worksheets are in the front, so you can take them if you want. I believe they're also posted on Ed. Let me know if that's not the case. We can fix it right here, right now. So but in absence of that, let's just get started. So we have this first problem, which is about solving this problem. P star is equal to min over x of y minus x infinity norm. Sorry, these are all vectors in RD, subject to some constraints. Actually, just one constraint. The one norm of x less than equal to some constant mu. And mu here is a constant which is greater than 0. Y here is fixed. X is the variable that you optimize over. And then for the sake of convenience, we're just going to assume that the one norm of y is greater than mu. Because otherwise you could solve this easily and get the optimal value of 0. Okay, so just assume that this cannot be solved. This cannot just set x equals y. Okay, so the first problem will just ask us to solve this in a simple numerical case. So we said d equals 2, right? X is a vector in RD, so let me just write that out. And we set d equals 2, and in particular we set y is equal to 2, 1, and then mu is equal to 1. And we're given p star is equal to 1. Okay? And now we want to find x star. Okay, so I wasn't here at the Tuesday's review session, but did you, for those of you who were here, did the TA give you time to work on the problem before going over solution? No? Okay. Well, let's just go over the solution. Unless you all would want time, but maybe I'll save the time for a later problem where it's more complicated, and maybe that would be better. Then I'll probably save time for a later problem. Okay, good. So we're given p star is equal to 1, right? So this is just a numerical example, so I'll go through it in as much detail as I can. So we're given p star is equal to 1. So this tells us that infinity norm of y minus x star is equal to 1, right? X star being the optimal solution. And this tells us like bounds for each of the coordinates of x star because we know y. So in particular, this means that x star 1, which is the first coordinate of x star, is going to be in the interval 1 to 3 because it cannot be more than one distance away from 2. Right, that's the meaning of the infinity norm constraint. And then x2 star is in the interval 0 to 2. Okay, these are bounds that must happen for x star. And because we know that x1 star has to be in 1 to 3, and we know that x star has to have one norm equal to 1, then we're just left with one choice, which is just take x star is equal to 1, 0. Okay? Because this is the only acceptable value of x1 star, and then that makes x2 star equal to 0. Yeah. I mean, that's exactly what we're doing here. This is just a particular way that you carry out this calculation. Okay. Yeah, that's exactly what we're doing here. Yeah. Okay. So B is slightly more complicated. So we're given, again, d equals 2. And we're given y is equal to, again, 2, 1. And let mu this time equals to 2. And then we're given t star is equal to 1 half. Shoot, is there any better chalk here? Okay, I guess not. That's fine. Okay, so here p star is equal to 1 half. And so again, we're going to go through the same machine. Okay? Y minus x star, infinity norm, less than equal to 1 half. This gives us that x star 1 is in the interval 2 minus 1 half and then 2 plus 1 half, so it's 3 halves, 5 halves. And then x2 star is in the interval 1 minus 1 half and then 1 plus 1 half. So that is 1 half, 3 halves. Okay? And so if you'll notice that taking the, and so you'll notice that mu is equal to 2, so that means the L1 norm of x star is less than or equal to 2. And you'll notice that the left-hand side bounds for x1 star and x2 star add up to 2. So that must be the solution. And so in particular, we have x star is equal to 3 halves, 1 half. Go for it.
On the left board, why are you writing the constraint as an equality? Sorry, the objective as an equality, but then on the right, you're writing it as a less than or equal to?
Oh, yes, that's a good point. Yeah, this is a typo. Equal to. And this is the objective evaluated at a particular x star. Sorry, I should put vector signs everywhere. And so that's how you can conclude it's an equality. Otherwise, it has to be even greater than or equal to. Okay. Questions? Go for it.
Can you explain again, how are you getting x star after x1 and x2?
Yeah. So, well, are you just asking about this case, or? Yeah, sure. So, I mean, the way we do it is slightly different in both cases, and it's kind of tuned because the problem has very nice numbers to make this work. So, in the first case, we know that x1 star has to be at least 1. And in particular, the constraint that the L1 norm of x star has to be at most 1 will just make x1 star equals to 1. Okay, and that forces, because of the L1 norm constraint again, forces x2 star equals 0. Okay? The second one, it's we know that L1 norm of x star has to be equal to 2. And so if we take the minimum value for x1 star and x2 star, we know it's exactly equal to 2. So we cannot make any of them bigger than their minimum value. Okay? And so that gives us what x star must be. Okay. So now we're no longer dealing with examples. Let's just do the full problem. So in this one, we're given that, well, we're just given assumptions that y1 greater than or equal to y2 greater than or equal to all the way to yd, and they're all non-negative. Okay? And then tau is just a tau, and then some number which we call tau star. Tau star is such that y1 greater than or equal to tau star greater than or equal to 0, and we have this sort of mysterious looking equality, which is that sum from I equals 1 to d yi minus min of yi and tau star equals mu. Okay, so we're given that tau star exists. Apparently, you can prove that it always exists. I personally don't know how, but the exam will tell you that you can always prove that it exists. And we want to show that tau star will solve this primal, or will be the value of this primal problem, optimal value of this primal problem. Okay, and surprise, surprise, the goal of this problem overall is to show that this problem exhibits strong duality in a direct way without appealing to something like Slater's condition. And so we're going to compute the optimal primal and dual values and show that they're both equal to this tau star. Okay, that'll show that strong duality holds. So first, we're going to show that the optimal value of this primal problem is exactly equal to tau star. Okay, so how do we do this? We show that. Oh, sorry. I mean, we don't show it's exactly equal. We show that tau star is an upper bound on the objective value, and then we'll show at the end that everything's equal. Yeah. Okay. So let's define this w is defined such that wi, so each entry wi of w is equal to yi minus min yi and then tau star. Okay, so that means that the sum of the wi's is equal to mu. And in particular, in particular, this shows that the L1 norm of w is just equal to the sum of from I equals 1 to d of wi. And then by definition, this is equal to mu. Okay, so that's the second part of part C. But the first part of part C asks you to show that y minus w infinity norm is exactly equal to tau star. Okay, wait. So before we do that, let me just first emphasize that this equality over here shows that w is feasible for this problem, which I probably should have labeled, but it's the only problem that we're going to, it's the first primal problem that we're going to consider, which has p star equals to whatever. So w is feasible for this problem. Okay, and so now we're going to compute its objective value, which is going to give us something. It's going to give us tau, tau star. So computing its objective value, we get y minus w. These are all vectors. Is there a question? No? Okay. Okay, so we compute y minus w infinity norm.
When you said that
Yeah.
w is feasible for that problem, what
Yeah.
do you mean? Because we're optimizing over, in this problem, we're trying to find R star, right? Are you saying
R star? What is R star? Tau star.
Oh, I thought it was, tau star.
No, so tau is just some like number that we know, like tau is just some number that has these properties. Okay, this property, y1 greater than equal to tau star greater than equal to 0, and then mu is equal to this thing over here, which is a.
When you say w is feasible, you mean you replace y with w?
No, replace x with w. X is the optimization variable here. Look at problem 1 on your worksheet. There's an x in that problem. That is your optimization variable.
Okay, thank you. Sorry.
Sure. Okay, so now we're just going to compute this infinity norm and just compute the objective value of w. Okay, and this will give us This is just the max over I of yi minus wi. Okay, and so if we sub in wi in over here, this is defined as yi minus something else. This is just equal to max over I of min of yi and tau star. Okay. So the first thing is that because both of these quantities are greater than 0, the absolute value doesn't matter. So you can write this as max over I min of yi and then tau star. Okay? And so because we know that y1 is greater than, okay, so we know this relation, right? y1 greater than equal to y2 greater than equal to whatever, greater than equal to 0, right? And because y1 is greater than all the rest, we know that min of y1 and tau star is greater than min of like all the rest and tau star, right? Because the value can either be yi or tau star. And so, yeah, and because like you can pick y1, then you might as well pick y1 and get the largest value. Okay, so then this is just equal to min y1 and tau star. Okay, I mean the formal way you prove this is you show that the min function, min of the first argument, comma tau star, is like a monotonically increasing function. Okay. Yeah, I mean you prove that this function, right? So max of yi, so max of I of yi is just equal to y1, right? Because of this assumption. Right. So then you prove that this function, something y maps to min of y and tau star, is monotonically increasing. Therefore, doesn't change the maximizer. Or monotonically non-decreasing.
Why would that not be the max?
I mean, this is a theorem. This like if you have a problem and then you apply a monotonically increasing function to the objective, or non-decreasing function, then it will not change the location of the maximizer. Yeah, this is a theorem. Okay, and in the last step, we know that this is min of y1 and tau star, and so we know that y1 is greater than or equal to tau star, and so this is just equal to tau star. Okay, and the claim is proved. So in particular, we've shown that W is feasible for this primal problem. We've shown that the objective value of W is tau star, and so we know that there's a point which gets objective value tau star. So that means that P star is less than or equal to tau star. Go for it, yeah.
I'm sorry, I don't want to take up too much time, but like I still don't really understand how you got the max min is equal to min.
This is max over I,
Right.
min over yi tau. Okay, so again, we take a monotonic function. Okay, so again, max over I of yi is maximized at I equals 1. Right? Because we have this relation that y1 is greater than y2, or whatever. Yeah. So then we apply a monotonic function. This is the monotonic function to every element of this sequence. Right? Like monotonically non-decreasing.
Function
It's like a function of each yi. Right?
Okay.
So I say it's like a scalar to scalar function.
Okay, so we're looking at it as a function of y,
Yes.
not of how.
No. No. Yeah. And then because it's a monotonically non-decreasing function, it should not change the location of the optimizer. And because it does not change the location of the optimizer is still y1. And so you can just plug in y1 over here.
Why? Because it doesn't change the location of the optimizer. It's the optimizer y1.
Because the optimizer, without considering this min of whatever given tau, is just still y1.
Like just max I over yi.
Yes.
Okay, so then where did that tau star come from in the end?
Because we have this is a monotonic function. which introduces tau star. Tau star is just some constant.
Okay. And the minimizer in this case is,
There's no minimizer. I mean, we're not talking about minimizers here.
or like the maximizer.
It's still going to be y1, or index 1 if you want to be formal.
Okay.
Yeah.
Thank you.
Good. Okay. Okay. And so, yeah, and so therefore we get p star less than equal to tau star. Okay. Oh, wait. Sorry, I should push this one up first. Okay. Now we want to derive a dual of this primal. Okay. And yeah, and so it explicitly tells us, although we should do this anyways, it explicitly tells us to introduce some vector valued optimization variable to replace this L infinity constraint. What do I mean by that? I mean that you can write this objective y minus x as equal to the max over z such that the one norm of z is less than or equal 1 of z transpose y minus x. Okay? This is given by Holder's inequality, but more than that, you should have seen it a few times in, for example, discussion and homework. Okay? So now we're going to do that. Now we're going to use that in order to compute the dual of this primal problem. So yeah, so the way we do this is we just say that p star equal to min over x. And now we're going to use this max representation of z such that one norm of z less than or equal 1 of z transpose y minus x. Okay, so this is just, again, a function of x. And then you also have some constraints in x, which is just that, what is the constraint? The L1 norm of x. Is less than or equal to mu. Okay? Good. So now we're going to go back to thinking about when we first defined the Lagrangian. So when we first defined the Lagrangian, it was defined as the thing such that p star is equal to min over your primal variable, max over your dual variable of the Lagrangian is equal to p star, and then max min is equal to d star. So if you remember, that's because we could introduce a dual variable such that the maximization would so basically we just introduce a dual variable, add it to this maximization, and then take the dot product of that dual variable with the constraint, and it will give us the Lagrangian. So we're going to do a similar kind of thing here to form a Lagrangian for this kind of problem. Just obtain that p star min over x max over z such that one norm of z less than or equal 1, and then lambda such that lambda greater than or equal 0 of z transpose y minus x plus lambda times this constraint.
Wait, if we're taking
Sorry.
Lagrangian,
Let me finish, please.
sorry.
Yeah. Mu minus one norm of x. Okay. And why does this work? It works because if we separate out this maximization, then it works because if we separate out this maximization into maximization over z and maximization over lambda, and we consider first the maximization over lambda, if this thing is not if this thing is positive, right? Then if that thing is positive, then the optimal value of the Lagrangian will, or this maximization will make the thing inside infinity. Okay, and so we don't want to choose an x which makes the thing inside infinity because we're minimizing over x. Okay, and the other constraint is like inherited from the previous expression. Okay, so the step we did here is just similar to how we first derived the Lagrangian as such that we could write p star is equal to min max of whatever. Yeah. Okay, go first.
Why isn't it lambda times L1 of x minus mu?
Because I made a typo. Thank you. Yeah. Yeah. Go for it.
What about the bottom constraint that like the one norm of p less than 1?
What about it? It got inherited from here. Yeah.
Why don't we put that in the Lagrangian?
We could. We could. That's just another thing. But because the final expression still involves this one norm of z less than equal 1 as a constraint, we just choose to keep it here. Yeah, that's just some problem solving kind of idea. You could definitely do it and then put it back at the end, but we do it this way. Yeah.
That makes sense.
Yeah, good. Okay, so then what is the dual? So we should know that d star is equal to max over z, such that one norm of z less than equal 1 and lambda greater than equal 0 of min over x c transpose y minus x plus lambda in one norm of x less than 1, or one norm of x minus mu, and parentheses. Okay, so this thing is your Lagrangian, or kind of is your Lagrangian. Let me make sure I can write this properly. I'm going to write this as Lagrangian Lx z lambda, right? And then d star is just max over your dual variable, z and lambda, min over x of your Lagrangian. Okay, so this is like familiar territory. Yeah, go for it.
Can you explain what happened to the max and the p star? How you're like reformulating it into
Sorry, can you repeat that?
So like in the p star, you have
Yeah.
min over x, max over z and lambda.
Yeah.
And then in d star, you have max over z. And you just like flip the two or like.
Yes, that's the definition of the dual problem. Yes. Okay. Yeah, go for it.
So I think like generally when we discussed like flipping it before, it was with the Lagrangian having absorbed all the constraints besides the dual variable one.
That's a good point. You can still keep some constraints out. This is like, I mean, they call it sometimes a partial Lagrangian.
Wait,
Yeah.
is that always true? That like you can just
Yeah, as long as you're able to solve this maximization problem efficiently, then yeah, you can do that.
like
Yeah, I mean, yeah, you can always do that. But the resulting dual problem might be harder to solve. That's the thing.
okay.
Yeah, yeah. In this case, we're kind of aiming towards this target where we have this L1 constraint on z and this lambda greater than 0 constraint. We already are aiming towards that, so we don't have to simplify any further. Yeah. Yeah, good. Good questions. Yeah. Okay, so how do we do this minimization? What's the time look like, by the way?
110.
Oh, I'm already over. Oh, shoot. Okay. Yeah, so then I guess I cannot give you time to work on this. Okay, so we want to show that this minimization is just equal to, so let's just say g of z and lambda is equal to min over x, and just min over x, xc lambda. We want to show that this is equal to, what is it? Z transpose, what is it? Z transpose y minus lambda mu. If infinity norm of z less than equal lambda, and then minus infinity either way. Okay, this is the claim we want to make. And Let me just pick up another chalk. Is there another chalk here? Okay, there's no other chalk here. Probably this is the best. Okay. Yeah, so we want to show this. And the thing that we want to show basically is just what happens if we minimize this over x. So let's just rewrite out the Lagrangian. And just write it in a term which is more amenable to this kind of form. So it's just Z transpose Y minus lambda mu plus lambda times 1 norm of x minus lambda times 1 norm of x minus Z transpose x. Yeah. Oh, there's none of that, yeah. Okay? And so we want to show that the minimum over this thing is either infinity or 0, depending on these cases. Okay? Can you both scoot in a little bit or something? So now we just want to solve this problem. Min over x of lambda times 1 norm of x minus C transpose x. Okay, so this thing is like, okay, so normally one could take the derivative side to 0 solve, but that's not possible in this case just because the 1 norm is not differentiable. And so we've got to show some like lower bound and show when it holds like with equality. Remember that this is what we did when we're, for example, computing dual norms, or like this L1, L infinity duality, or more particularly Holder's inequality, which we're going to invoke here. So in particular, I'll just call this thing F of Z comma lambda. XC lambda. Okay, so by Holder's inequality, so remember Holder's inequality will tell you that x transpose Z less than equal to 1 norm of x times infinity norm of Z for all x and z, and this is sometimes met with equality depending on, I mean, you can find an x which will always make this equality. So by Holder's inequality, what we have is fxz lambda greater than equal to, just by this invocation of Holder's inequality, we get greater than equal to x times 1 norm times lambda minus z infinity norm. Okay? So first, suppose that lambda is greater than equal to infinity norm of z, greater than equal to, yeah, that's fine. Then this thing is greater than equal to 0. Okay? And because that's greater than equal to 0, min over x of f is just equal to 0, because you can meet this with equality by picking x equals 0. Okay. So second, if lambda is less than infinity norm of z, then what happens? So if lambda is less than infinity norm of z, then this second term, or this term in the parentheses is negative. Okay? And because this term in the parentheses is negative, then if we pick, for example, x hat, which achieves equality, in Holder's, then f of alpha times x hat alpha here being a positive scalar, and then lambda and z and lambda is equal to alpha times L1 norm of x hat plus, what is it? Alpha times L1 norm of x hat times infinity norm of z minus mu. Okay? And just by sending alpha to infinity, we can get f hat, or just like f is minimized at negative infinity. So this limit will show that min x of f equals to negative infinity. Okay? So this in particular will show, these two calculations in particular will show that it will show this it will show this. Because either if infinity norm of z less than equal lambda, then we get the first case, and then the third term in this Lagrangian will go to 0, and otherwise it's negative infinity. Okay, so that's that calculation.
And so then you incorporate that condition as a constraint.
Yeah. Yeah.
Okay.
Which part of this problem are we on now?
That was part D.
Okay.
Yeah. Okay. So now you're given part E. Let me. Was that? Because like this thing was just a function of alpha, right? And everything aside from alpha is this term is negative, right? And because that term is negative, if you just multiply alpha and then you send alpha to infinity, you're going to get negative infinity. Maybe I made a typo. Where is it? This should not be negative. Sorry. Yeah. Sorry. Wait. Okay, where did I make a typo? I probably made a typo several places. Let's see. Sorry, this is lambda minus infinity norm of z. My bad. Okay, and by assumption, that thing is negative. Yeah. Okay. Moving on. So we want to show that, sorry, I'll be no more than 10 minutes. Probably like 5 minutes, yeah. So we want to show, okay, so now we computed the dual, right? This dual, let's just say, is like given by, I won't rewrite it for time constraints, but it's given by equation 4 on your paper, your worksheet. So now we want to define a dual feasible point, which achieves the dual objective value of tau star. Okay, and that'll show that because that shows that d star is less than or equal to tau star. And in particular, d star is less than equal to tau, or greater than equal to tau star. My apologies. D star greater than equal to tau star. We show that p star is less than equal to tau star. And so by weak duality, we can conclude that they're all equal. Okay? So actually, maybe for time's sake, I think for time's sake, I'll leave that as exercise to do part E. Because I don't think that there's any like optimization content. It's just algebra. So I'll leave part E to you because there's no it doesn't actually test like course concept. It just like is algebra exercise. So I'll leave that to you. And then for part F, we know that so from part D basically just gives us that there exists z star, lambda star, such that, so feasible for dual, and then obtains objective value, dual objective value, equals, dual objective value is equal to tau star. Okay? And because the dual objective value is equal to tau star, we know that there's a feasible point for for the dual problem, which gives us the feasible point for the dual problem, which gives us objective value tau star. So that means that tau star less than equal to d star. Okay, and like my work on the middle board shows that, oh, maybe I erased it, but yeah, probably erased it. But in particular, this shows that, I mean, because we have weak duality, we have that d star less than equal p star. Then we already showed that p star is less than equal to tau star. This is part C. Okay? And so what does this show? This shows that tau star is equal to p star equal to d star. Okay? Because it's like a sandwich, right? You have tau star at both ends, and then everything in the middle has to be equal to tau star. Okay. Yeah, so that's part F, and that's problem 1. Let me just quickly... Maybe because this worksheet has like so many problems on reformulation, I'll just probably skip problem 2 for the sake of time. Yeah.
Okay.
Go for it.
So technically in part F,
Yeah.
we're not saying that we're not relying. Like I think it is technically true that tau star is the solution to the dual because of strong duality, but technically we're not using that fact.
We're not using. Yeah,
We're
exactly.
saying that it is a feasible point.
Yes, exactly.
Okay.
And then in part F, we show that it's a optimal value. Yeah.
Okay. Yeah.
Okay. Yeah. Sorry for running over time. We could take questions at the end, but.
Okay, so we'll now skip to problem 5. We'll go back to problem 3 and 4 later. Apologies for that. Yeah, so let's look at 5 first. So this is an LP problem where the first question asks us to, one second, where is the chalk? Yeah, so the first problem is, yep. So the first problem asks us to plot the feasible region. Now in this problem, this is so yeah, as you can see, it's much easier than the first problem. Okay, so so the x1 axis and x2 axis. Now we're just plotting based on each constraint, we're plotting the feasible region. So we go one by one. So so for all x1 greater than 0, it's oops, sorry. Okay. So this is everything from this region to so basically from this axis to the right. So that's x1 greater than 0. So everything on this side, right? So x2 greater than 0, it's everything up from this axis, right? Everything up there. So x2 greater than 0. Now the third one is 1 minus x. Okay, so we just plot. So we just plot this this constraint. So 1, 1. Now this is the constraint. So 1 minus x1 minus x2 smaller than 0. So everything up top right on this from this constraint, this region. And the third one is x1 smaller than 3. So again, something like this. So this is 3, x1 smaller than 3. And the last one is kind of symmetric, right? So 3x, yeah. So x2 smaller than 3. So the feasible region is just this this region. Yeah. Any questions? I think it's pretty straightforward, right? So I just plotted this region, and so let's go to the second problem. So the second problem asks us to find the optimal p, so optimal objective value. So there are, well, in this problem, because we have a linear program, so we know the optimal value has to be on the vertex of this region, right? yeah, so we can either evaluate on each of the vertex what's the optimal value, and we can find well, basically everything on this line has to basically evaluates to the same optimal value, which is 1. Another way to think about it is so this, note the objective value, objective function is just x1 plus x2, right? Another way to think about it is we can basically plot this line, right? So if we take c equals this constant to be 0, then it's this line, right? Yeah, so x1 plus x2 equals 0. And we can basically kind of move this line up and down, and whenever it first intercepts with this region, it becomes the optimal value. That's another way to think about this. Right, so the first time it interacts with this region, it's on this line. So it's another way to think about this problem. Okay. Yeah, so again, yeah, so this optimal value we find is everything, all the points on this part, which evaluates to 1. So that's the answer for this question. Yeah, any questions on this one? Okay, so let's go to numbers. So question 6, going to the next one. So this question, we have a QP, a quadratic program, and we just have this objective function, which is x transpose m x to b. Any questions? Yeah.
What is the this problem in problem 5?
Mm-hmm.
This line here is completely outside of the feasible region.
Oh, you mean this line?
Yes.
Oh yeah. This line is completely out. I'm just illustrating. So this line is just illustrating. So I'm just saying one way to find the optimal solution is to basically find. Basically, you can think of basically what we are optimizing is the C, right? And we can plot this line on basically plot this line in.
It's the level sets, right?
Yes, yeah, and you can basically by changing this C, we're actually moving this line up or down, right?
Okay.
And the first time it intersects when we move up, right? When we move this line up, it's like increasing C, right? The first time it interacts with this feasible region, then that's the minimum value we can get, which is the optimal value because we are minimizing. Just to illustrate. Yeah, this is not a constraint or not. Yeah, so just to illustrate. Okay. Yeah.
For question 5, can you explain that again? So you said you have your line x1 plus x2 plus c. So you're just moving it until you reach the feasible region?
Yes. Because here we are optimizing this x1 plus x2. I'm just calling it as let's say it's a c. We're optimizing, right? And we can always plot this line in this figure, right? It's just a level set.
So what's the value of p star?
P star. Yeah. So it's basically when we move this line up and interacts with this feasible region, which is this line, which is x1 plus x2 equals 1. So the optimal value is 1. Okay. Yeah, it's just a way to think about this. Another way you can always find, which it always works, is just evaluate on all the vertices, and you can find the solution that way. Okay, so any questions on number 5? Okay, we'll go to number 6. So just, so this is the objective function, right? So these two problems are, it's just asking you to about whether the objective function, objective value, optimal value you got is minus infinity or is it finite, right? So to think about this problem. To start, we can, okay, and also, so in this problem, we know that the format of this M, right? We know this, it's a very structured matrix. Oh, sorry. Yeah. Plus 3. It's a very structured matrix, and we can notice that this. Yeah. So this matrix, it's not full rank, right? Just from observation. Is this clear?
This is the dyadic SVD, right?
It's not an SVD. It's just so, but it's like you can basically you already have the basis for this matrix, right?
Okay.
So which is the E1. So this is E1, right? The E1 vector, and this is E3, right? So you already so.
Sorry. I remember at like the very beginning of class they were talking about something called like the dyadic SVD.
Yeah. So
Is that this or no?
it's not.
Oh.
Yeah.
Like,
It's,
what about this is not dyadic?
oh, it's just well, what you're talking about, I think, is how to express the SVD, right? So it just singular values, for example, singular values and the singular vectors. You can always say like so transpose, right?
Isn't this not one?
I think it is a dyadic
Oh,
SVD. It's just that for symmetric matrices, the left and right singular vectors, like the u's and the v's, are the same because it's got bigraphal matrix,
Right.
right? And so, and because of this lucky circumstance that
Yeah, it's
the vectors are unit vectors, like this 1, 0, 0, and 0, 0, 1
That's
are
right.
unit vectors. This makes it possible to
it's all yeah.
because
I'll
of
get
that they're orthonormal. So if like they weren't normalized or they weren't orthogonal, then you would not be able to say this.
Yeah.
It'd just be a regular diagonalization.
That's
But
absolutely
in this
right.
case, it's like
Yeah, because we wrote it. Yes. So in that sense, you're correct. So this, because these are normalized vectors, we can say that. But in general, if let's put the 4 inside, then you can't really say that because it's no longer normalized.
That makes sense. Thank you.
Okay. Yeah. So everyone is clear on this. So just from observation, so we have these two. So basically, this matrix is constructed from these two. So these two bases, right? So this is a 3x3 matrix. So we can already find this null space. Everyone agrees, right? Because we are missing one basis, right? We are missing one basis from this matrix, which makes it a not full rank. So M is not a full rank matrix, right? And here we are talking about, so we have this B. So for A and B, we know. So the question asks if the B is a specific vector, what's the optimal value for this particular objective function, right? So let's think about the at optimality. What's the condition, right? So this is the objective function. Let's just call it f, right? The optimality, right? So we can just take the gradient against with regard to x, right? So take the gradient, and then we can get 2m x vector, right? 2 minus b minus 2b, sorry, equals 0, right? So this is the just from at optimality. What this means is we know that if this problem has an optimal solution, then this mx has to be equal to b, which means b has to be in the range of m. But this is not always true, right? Because here m is not full rank, correct? M is not full rank. So what if b is in the B can be in the null space, right? So basically this means if we, okay, so in the first problem, in A, so if B is in the form 1, 2, so B is this specific vector, then we know this this vector cannot, it's basically in the is in the null space, right? Just looking at this formulation. So this means we cannot construct an X that maps it to B, right? Which makes this objective function like we can. So this will evaluate to minus infinity. We can always construct. In fact, we can construct an X. So to see that, what we can do is, let's say, let's use. Let's just use the E2 in the null space, right? So we can take X. Let's just take it for, let's say, alpha, right? For some alpha. Right, and then we can basically plug in this formulation, and because it's in the null space, right? This will evaluate to 0. You can evaluate this, and this part will evaluate to 0, and this part we know we can basically plug in, and this becomes this whole objective function becomes minus 2 alpha, just minus 2 alpha, right? We put this X in this objective function, and we get this fx equals minus 2 alpha. Because we said this alpha is like anything, right? We can put any alpha for this particular value for this X, which means we can just move this wherever we want. So this can evaluate to minus infinity if we want, right? Yeah.
Is there a way to see from the SVD what the range of M is?
SVD? Yeah. So it's already in the as you pointed out earlier. This is already in the SVD form, right?
So can we look at the range of how do you see the range of M from the SVD?
Oh, well, it's actually.
Is it the span of those two vectors?
So this is the basis, right? So these two are the basis. So what in the range of M will be any combination, linear combination of these two bases.
Oh, okay.
Right?
And we could just say B is not in that span.
Yeah.
So, okay.
Yeah. Exactly. B is not in the span.
That makes sense.
Yeah. So we're taking X to be in the null space, in this case.
Okay. Thank you.
Yeah. So for A, hope it's clear. For A, this is minus infinity. And for the second problem, where B is no longer, so this is A. So for B, so B is, 1, 0, 1. So this is precisely within our within the span of M, right? This can be obtained by these two bases, 1, 0, 1. Yes.
How do we know that M is symmetric?
How do you know it's symmetric? Because the way it's constructed. So to see that, you notice here it's like a vector times its transpose. So it's in this form, right? A transpose, and this is always symmetric, right? Well, you can just take this. It values to itself, right? Yeah. Okay, so for the second problem, B is 1, 0, 1, this vector. And this is within the span of M, right? So in this case, it's no longer minus infinity. You can actually construct, you actually solve for this x, right? So x becomes, so you can actually construct based on this optimality condition, right? We can construct this x, the corresponding x. So it should be like 4. Yeah. Oh, I think it's too small. Okay. Let's. So this becomes 1 over 4, 0, 1 over 3. Also, don't forget, because here M is not full rank. So we can always, again, we can plus anything. We can add anything from the null space, right, in the solution, because it doesn't contribute to the solution. So x is of this form, and then you plug it in. It doesn't evaluate to minus infinity. Basically, this thing will cancel out. Yeah. Yep. Okay. Yeah. So that's for the set. Please.
Do we have to do the part with x, or can we just show that B is in a range space?
Yeah. In this problem, yes, because we don't ask what's the specific value for P star is.
Okay, but if you wanted to find that.
Yes, it's possible. You can just plug this in.
Okay.
Yeah. Yes, please.
Just to make sure, so in part A, the reason we got negative infinity was because B had a value that was not in the span of M.
Yes.
So we kept, if we were doing minus 2B transpose some x, that value kind of goes to negative infinity.
Yes.
That's why.
Yeah. So, are you asking about this? How we come up with the?
Yeah. The alpha 1 thing.
Oh, alpha 1. Yeah. So basically, what I'm just saying, like, let's just choose. So basically, choosing a vector that is not in the. So basically, in the null space, that is not in the span, just as you said. Yeah. So we can plug this in, and we find it's in this particular format, -2 alpha, and because we say it's for some random alpha, and so we can, adjust this alpha to be whatever value we want, which evaluates to minus infinity. Okay. So, any questions for 6? If not, I'll go to reformulation. Number 7.
What's the combination for part B? So the answer is that go to negative infinity, or we have a finite number?
Yeah.
Or we have
Yeah.
a finite number?
Yes. So for the second problem, for B, we do have a finite number.
Okay. Which
Yeah.
number?
Oh, I didn't plug this in, but you can plug it in. I think it will evaluate to, -1 over 7.
Oh, okay.
Yeah. So for B, it's finite. For A, it's not. It's minus infinity. Okay. So for 7, okay, I'll write it here. Okay. So for A, we're trying to reformulate this problem as an SOCP. Okay, so the original optimization problem is the minimum over x and of the maximum over I from 1 to m. And the objective is ax minus b y yi Yeah. So the 2 norm of this vector. Yeah. Actually, so from inspection, we can already see this form is very close to an SOCP constraint that we want, right? So it's always so for these kind of reformulation problem, it's like the first thing like you want to think of when you see something like of this form is to use a slack variable or like epigraph reformulation. So in this problem, we can convert this problem by introducing like we just used an epigraph reformulation, which is we introduce an variable t. So minimum over, so we introduce another optimization variable t, and so we optimize. The objective becomes t, and the constraint. Previously, we didn't really have a constraint here, and now because of the epigraph reformulation, we want to. So we have a constraint now, which is max I equals I from 1 to m, and this is ax minus b yi smaller than t. Right? But this is closer to an SOCP constraint, but not quite. But notice that it's this constraint is we're taking the max over like m number like we're basically taking the max of over this m constraints, which is equivalent to saying we optimize t such that we are just taking we're just expanding this maximization over the m. So we are explicitly writing out the m constraints, which is ax minus byi. Yeah, this is a vector smaller than t for I from 1 to n. Yeah, so this becomes an SOCP constraint now. Yeah, this becomes the standard form. So that's how we reformulate. Please.
On these problems, when they ask for like something in the form of like an SOCP or like a, I don't know, like QC, QP, do those want nsnr?
As long as I think if you write in the standard form, you'll be. I think you'll get full credit once you write.
Do they want it in like
Canonical form? Are you talking about? I don't think so. Do we? Okay, so that's A, part A. So part B, I think part B is pretty short, so I can just write here. Yeah, sorry about the format. So part B. So part B is so we have this optimization problem that is very close to a QP, but the problem is A is not a PSD, right? It's not a positive semi-definite matrix. So, but we do have the format for A, right? It's 1 0 minus 1 1. That's the format for A. And and we have a hint here. It's saying like you can write this as you can modify this objective to make basically to make this this A matrix into something that is symmetric, right? And to do that, it's you can actually you can. If you cannot do this by just looking at it, it's we can write it the full the full derivation, which is we can just write out what's the what's the expression for x transpose A x transpose. We can just write it out, and this becomes like if you fully expand it, x1 minus x1 x2 plus x2 squared, and this is actually like a very symmetric format, right? And so the hint is saying we can write it in a symmetric format, right? And we can do that by let's just because this is the format we want, right? x1 squared minus x1 x2 plus x2 squared. So we can do that like so. This is the B, right? We know it's a symmetric matrix, and x1, x2, we have these. Oh, oops. Let's just do it like this. x1, x2. And we know it's symmetric. And also, because of x1 and x2 squared, we know this has to be 1 and 1. Right? And for these two, because it has to be symmetric, you can basically, you can because it's constrained to be like, these two numbers have to be the same, right? You can just plug it in and you can maybe set an unknown, like an B or something and solve it. You get like this thing. This is the same. And also because notice here, this is always greater than 0. So this is a positive definite. Now this thing becomes a quadratic, becomes a QP, quadratic program. Are you talking about this constraint or this constraint? This one. This one. Yeah. So so for here, so basically we're just saying, recall the epigraph reformulation is we are doing some minimization problem, right? Minimization over fx, right? So the max of this norm is our fx in this case, and what we are doing is just we're simply plugging in the epigraph reformulation, which basically just move this part into the constraint. Yeah. Is this clear? Please.
Sorry, this is a really silly question. How did you get to those PSD?
So this is greater than 0. X1 minus x1 x2 plus x2 squared has to be greater than 0. Are you asking about this part? Yeah. So this part is so we can we can write one more step, which is like x1 minus like a half x2 squared plus 3 over 4 x2 squared, right? And squared. Well, has to be, yeah. Right? Because it's like 2 squared, so it has to be greater than 0.
Okay.
Yeah.
Thank you.
Yes.
Can you explain your intuition with why you said x transpose ax to equal like x1 squared minus x1
X. Oh, this part?
Yeah, explain.
Oh, you simply plug this in, this x1, x2. Yeah, just simply plug it in. It's not too complicated because it's 2D, right? Yeah. Any questions? Yeah. If not, we can. Yeah. Tim, you can go over.
Okay, I'll cover problem 4, which is Nguyen's method. So, okay, for problem 4, part A, we want to find the optimum value x star equals to argument of f of x, which is just x to the 4th power. And it says we can just look at this visually. So x to the 4th looks something like this, and you know that the value of this function is always going to be greater than or equal to 0, and it reaches its minimum at exactly 0. So the answer is 0. Does that make sense to everybody? Okay, so for part B, now this is a little bit more interesting, and we want to analyze the performance of the Newton's method on this problem. And we want to find the minimum steps. Okay, so what we have now is that, so the problem gave us the scalar form of the Newton's method, which is xk plus 1 equals to xk minus like this. And if you look at the matrix form that you learned in class, you will see that it's like pretty similar, right? Instead of this, you have an inverse with the Hessian. Anyways, okay. So now we can start trying to analyze this. So let's find out what these value is. So the first order derivative of the function is just 4 to the x cubed, and for the second order derivative is just 12x squared, and then we can figure out exactly what our update rule is. And our update rule is k, and then you do this divided by this. So let's write it out. And this is just xk, which is 2/3 xk. Okay, so far so good? Sounds good. So now let's find out what xk exactly is. So we know the update rule. That means that we can figure out the solutions to like what exactly is sk given the initial state, right? So we have, since we are at every step we're multiplying by 2/3, and that means that we're basically just starting from x0 and we multiply by 2/3 for exactly k times to get to xk. Make sense? Sounds good? Okay, so now we want to analyze our problem, which is that we want to see what is the minimum number of Newton steps that gets us to within epsilon distance from the true optimum. So we analyze so the problem actually just tell you that we want to basically solve for this thing. So how many steps does it take to get to a distance epsilon from the optimal? Okay, and so now we know that optimum from part A is just 0. So we're basically just trying to solve for xk. There's this, and we have figured out what xk is, and we can just plug it in. So we plug it in, and now we want to solve for k. So we need to simplify this a little bit more. So from here you can see that 2⁵ to the k is always going to be positive, so we can just factor it out. Oh. Okay. And now we need to take the log on both sides. So we take the log on both sides. We get k. The reason why we are able to take I'm actually skip the step here. I want to get k on one side, so I want to divide by this value, so the absolute value of x0 on both sides first. Okay, and now we take the log. The reason why we can take a log here is because the log is a monotonically increasing function. So the relationship between the two sides remains the same. Okay. And now all we need to do is that we can just isolate the k here. So we want to divide by log 2/3 on both sides. But be careful because log 2/3 is a negative value, right? Because the log function looks like this, where like this is 1. So it's actually 2/3 is actually a negative value. So we need to flip the signs as we do this. So k is actually greater than or equal to log 2/3. So now we figure out where our a has to be greater than this value. So what does that imply about? So the question asks, what's the minimum step that it takes for us to get to within this distance? So this right here could be not an integer, right? So we want to make sure it's an integer because when you run algorithm, it's discrete number of steps. So we would just say, okay, so the final answer k is just the ceiling function, which is just rounds the value to the nearest integer, rounds up actually. So of this, it's kind of ugly, but that's the minimum number of steps. So anybody has any questions? We will answer your questions after class. Feel free to come up as well. Good luck on the exam, guys. You guys are going to do great. You guys got it. Hope you guys enjoy 127. Or actually not quite done yet, but because you guys have a final, but you guys got this. Good luck. Make sure you get a good night of sleep. Like for me, I would just sleep instead of studying. That's my advice, but yeah.